Enhancing situ reductive dechlorination is the process of modifying chemical, physical, and biological conditions in the aquifer to stimulate the microbial degradation of contaminants under anaerobic conditions to harmless end products, for example, carbon dioxide or ethene. ERT commonly is used to treat dissolved phase plumes downgradient of source areas, but also can be designed to treat CBOC source areas, including those that contain dense not aqueous phase liquids. ERT is the process through which chlorinated atoms attached to an organic compound are sequentially removed under anoxic conditions. Application of ERT is comprised of biostimulation and sometimes bioaugmentation to modify existing geochemical and biological conditions. Biostimulation refers to the introduction of an electron donor into the aquifer for stimulating microbial growth. The carbon source, it is used as food by native microbes, which in turn produce hydrogen through fermentation reactions. Bioaugmentation refers to the introduction of microbes, which may be required at some sites to accelerate the acclimatization and biodegradation process if the existing microbial population is not adequate at the onset of treatment. Abiotic reductive dechlorination is a chemical degradation reaction where a chlorinated hydrocarbon is degraded by reactive compounds such as metal sulfides. By definition, the reaction is not microbially mediated. Direct anaerobic reductive dechlorination is a biological process where microbes receive energy and grow through sequential reductive dechlorination. In this reaction, chlorinated compounds serve as the terminal electron acceptor and hydrogen serve as the electron donor. Aqueous compounds are highly soluble, therefore are consumed in a relatively short time. For example, ethanol, benzonate, and syrup. Slow-release compounds tend to have low solubility limits. Because they are less soluble, they persist much longer. Typical solid phase substrates consist of materials such as mulch, compost, and shielding. They are used either as a one-time amendment or in a biobarrier constructions, for example, humic acid. ERT systems may be applied to treat source zone areas and dissolve phase plumes considering the following. Source zones treatment. The objective is to either reduce mass discharge from the source zones or accelerate source mass removal. The dissolved phase plumes may be treated by employing a plume-wide restoration approach or, alternatively, using biobarriers. The objective of a plume-wide design is to treat the entire dissolved phase plumes over a shorter remediation timeframe. ERT is applicable at sites contaminated with CBOC. These compounds are susceptible to reduction under anaerobic conditions by either biotic or abiotic process and are generally ERT can be a very cost-effective technology if properly designed and applied. Similar to many in-situ remediation technologies, the most critical cost factors are associated with the contaminant mass to be treated, the nature and extent of the contamination. Full-scale implementation can typically run between 2 to 10 years depending on the approach taken and the extent of contamination. Treatment timeframes, however, can be decades for more complex remediation sites involving significant source area, contaminant mass, and large plumes. Primary factors that affect the duration are remedial action objectives, treatment methodology, presence of LNAPL, number of injections events required, ability to achieve uniform distribution and sustainable concentration of amendments in the aquifer. Case of study: comparison of in situ chemical reduction to enhance reductive dechlorination to treat dechloration in an aerobic aquifer. Two pilot tests were conducted that compared the rates of contaminant degradation as well as other biochemical processes of both processes. The site is Concord Naval Weapons Base in Concord, California. Soil and groundwater has been affected by a discharge Dechloration. The affected aquifer consists of unconsolidated silts, sands, and clays. The ERT pilot test used buffered emulsified vegetable oil substrate, which was augmented with dechlorinate microbial concern. Sodium lactate was added to the injection water to condition the water prior to bioaugmentation. The hydrogen ion activity substantially affects the biological reductive dechlorination has been demonstrated to be inhibited by low pH conditions. Below pH of 6, the degradation rate of CAs begins to decrease, and at pH of 5, stops degradation. As highly reductive conditions were established, rapid reductive dechlorination of the dechlorating was observed in both of them. Notable differences were observed in the production and degradation of chlorinated products.